Good morning, all my AP Chem students. I hope that you're having an awesome day. Today we are going to continue in Chapter 5, talking about ideal gases. And again, the fundamental characteristics, you should find this page in your notes, of an ideal gas is that the volume of the individual gas particle is not important. So you need to make sure that you understand, again, we talked about if we are at STP, that the volume, whoa, that's a nice color that I'm using, that the volume would be 22.4 liters, but we aren't necessarily always at STP. And then point number 2, the force among the particles is not important. Remember that we are taking a look at the forcing being the intermolecular attraction or repulsions between molecules, and we talked about this the other day. Um, if, if this were important, then Dalton's law of partial pressure is equal to, pressure 1 plus pressure 2, and so on, then we wouldn't be able to say these statements because there would be a force of attraction there. We talked about how the pressure of this gas plus the pressure of this gas equals our total pressure. All right, now we're going to talk a little bit about mole fraction. All that is the ratio of the number of moles to the total moles in a mixture. We use the Greek letter chi, which looks like an X, and to show that mole fraction is shown with chi, saying that the individual mole, remember N is for the number of moles again, is divided by the total number of moles in the mixture. So very similar to Dalton's law, partial pressure, it's directly related to the number of moles. Well, if it's going to be directly related, you should also recognize that chi is going to be equal to pressure 1 over the total pressure. Now, if you remember Pivner, the reason that we can say this is we know that PV equals nRT, and so if I take out the number of moles and I take out the pressure, I'm going to have this constant. And so that's going to cancel out anyway, so it's not anything that we have to worry about. So our result then is that we can say that if these two substances are equal to each other, then Dalton's law is going to say that pressure 1 is equal to whatever mole fraction you have times its total pressure. And that's something that you'll need to keep in mind when you start working out some of these problems. Now, remember that if we talk about kinetic molecular theory a little bit, this should make sense to you that, remember, these gas particles remain in constant motion. The collisions are independent. The energy is conserved. So that's why Dalton's law of partial pressure says that we can take all these individual pressures to find our total. Now this is what we did in class with our lab. You guys did it with a butane lighter, and you were collecting butane gas. So our source here, you can see as you take a look at this, this would be a catalyst. That's just speeding up the reaction. We didn't really have to worry about our catalyst. We were just dispensing through the butane lighter. And again, we were bubbling that through into our Florence flask, which are round bottom flask here. And then we were collecting our butane here. Now keep in mind again that we have a certain amount of water pressure that is happening here, vapor pressure, and we had to show that by correcting that due to the temperature. So gathering a gas by water displacement results in a wet gas, which is what we were doing in class. I'm not quite sure I used that terminology. So to find our total pressure, we had to take our pressure 1 plus the pressure of the water. Now in lab, we were trying to find the pressure of just the butane, so that's why we subtracted our values to get that correction factor. So vapor pressure of water is temperature dependent. Okay, going on to the next one. So kinetic molecular theory of gases, what I was just kind of referring to is trying to explain the property of an ideal gas. Volume of particles can be assumed to be 0. All right, particles in constant motion, the collisions of the particles create pressure with the walls of the container. Particles exert no forces on each other, and the average kinetic energy is assumed to be proportional to the Kelvin temperature of the gas. All right, great. What does all of this mean? Well, if we take a look at the ratio of the volume of the gases, we know that 1 mole of any gas is going to equal 22.4 liters. So that's where this 22.4 is coming from. Now, if I can develop a ratio between this, we can see that the spacing of the molecules is 9 times farther apart in the nitrogen gas. we can say that gases have approximately 1/10 the density of the same material in the liquid. So meaning if I were to put this nitrogen in a liquid, it would be 1/10 greater density than that of a gas. So it's just a ratio thing. We're just trying again to give some explanation for these ideal gas laws. This should be pretty straightforward for you to understand, is that this is directly Boyle's law. If I increase the pressure, I decrease the volume. And if you remember, Boyle's law was P1 V1 equals P2 V2, and that is a direct relationship. If this is going up, this one better be going down, and vice versa. So if I have a decrease in volume, how is this decrease in volume happening? And I have still, if that volume is going down, I have an increase in pressure. Well, what's going on in here? Well, if I increase this pressure, the volume is going to be decreased. So I have much more collisions that are going on here. Remember, they're happening independently of each other. So these collisions are causing more and more pressure. They are colliding with each other, moving together. They're colliding with the wall, and you have an increase in pressure. All right, so the effects of increasing temperature of a sample. And again, we are trying to say that pressure is proportional to temperature. Well, how is that going to affect this? Well, if I take a look at this, this is going to be true. Increase in pressure. Oh wait, this is the temperature is increased. Okay, sorry, I was looking at a different slide. So forget about this right here. I was thinking that the volume was remaining the same, and we do not have the volume remaining the same, as obvious in the picture. So now we have Charles' law. So if I take a look at Charles' law says that if I increase the temperature, I have to also increase the volume. Well, that's if I want to hold pressure constant. That should make sense to you. If I want to hold pressure constant, I have these molecules that are creating collisions. That's the only way I have pressure. Well, if I increase the temperature, I better increase the volume, because if I don't do that, I'm going to have more and more collisions over here, a ton more collisions, and my pressure is going to increase. Well, if I want to keep my pressure constant, I have to have more room for these molecules to collide with each other. If that doesn't happen, my pressure is not going to remain constant. So as I take a look at this, as I increase the temperature, I hope you're thinking about kinetic energy. That kinetic energy is also increasing. And so the kinetic energy means that there's going to be more collisions and there's going to be more force. So in order to keep this constant, I have to increase the volume. All right, now increased volume due to increased moles. So now on the other ones, I was keeping the number of particles constant. Now all of a sudden, I'm going to take this and I'm going to add some more moles. I'm adding more substance. So as the particles increase, keep in mind that I have constant temperature and pressure. All right. Well, if I want constant temperature and pressure to happen, I got to change some other variable, and I'm going to change my volume. So if I increase the number of gas particles that I'm doing here at the same temperature and the pressure, I have to increase the volume. There's no other way around that, according to the ideal gas law. All right, the root mean square is something that we aren't going to use a whole lot of. There's just a couple simple little things that you need to know with this. So from a kinetic molecular theory, remember we're talking about the collision of molecules and how they're creating pressure. The average velocity of the gas particles can be calculated. Found by the square root of the average of the squares of the individual velocities of gas particles. Keep in mind that the velocities of all gas particles are different because they all have different masses. So that is shown in the formula. It is all derived in your text on page 204 if you're interested. We are just going to use the formula. So this is used to determine the speed of a gas molecule. And this is in meters per second. And if you go all the way through this, this right here means the root mean square. That's what that is. Root mean square is equal to the square root, gas law constant. The only problem with the gas law constant here is we have to have it in different units. So our gas law constant for this is 8.3 0.3145, and that unit is joules per Kelvin mole. Now, because of this, like I said, we aren't going to be using this a whole lot. Again, obviously, if I have a Kelvin, my temperature has to be, I'm sorry, if I have Kelvin here, this temperature right here has to be in Kelvin. We are talking about speed, so that's why this is expressed as an energy unit. Joule is an energy unit. Okay, so if we take a look, the collisions with the walls and other particles cause change in movements. Again, we talked about that the particles move independent of each other. The energy is conserved. So they collide with the wall, they move in straight line patterns independent of each other, but as more and more collisions happen, you are increasing the pressure. You guys have all talked about this in terms of gases. You have all experienced this, that take a look at cheap versus expensive perfume. All right, cheap perfume you can smell right away. It doesn't stay with you very long. The molecules travel really fast. It's really light. If you have a better perfume, the molecules are heavier, and they are going to stay on your skin longer. They aren't going to evaporate as quickly, and so that all has to do with the collisions and the particles that are moving here. Okay. And as we take a look, it says the average distance a particle travels between collisions is a gas sample called the mean free path. And again, this is going to be determined. Not very good at writing on this thing yet. I'm writing on a little bamboo thing instead of my smartboard, so I get rid of that pounding that you guys were talking about. It's determined by the volume, it's determined by the temperature, and it's determined by the number of particles. So the number of gas molecules that you are going to have, and it's also determined again by the pressure. Now all of these affect a gas, and that's why we have to take them all into consideration. This is usually a really, really small distance, and gas molecules do move fast. If we talk about the root mean path, oxygen molecule in your book talks about that it can move from Minneapolis to Detroit in an hour. Well, is it really moving that fast? No, because there's collisions and everything like that, but that's how fast they really can move. Okay, I think we are going to stop right here. Oh my gosh. Please tell me I was recording.